All right, guys. So we have chapter 29, sources of magnetic field. So in this chapter, we're going to continue our investigation of magnetic field, but we will look at mostly calculating the magnetic field rather than magnetic force. And the magnetic field is due to one or two different type of sources. Could be a moving charge, could be a current element. We're going to see, and we're going to be able to solve problems involving sources of magnetic fields. In this picture over here, you can see it's an MRI machine. MRI machine actually uses very powerful magnet inside to map uh, the organs of a patient. The idea here is that it creates a magnetic field that can go through your body and make the protons of your body to align with the field, with that external field. And then there's a radio frequency signal introduced, which disrupts the proton from basically makes it move from its orientation. And when the radio frequency is turned off, the proton then goes back, basically try to realign itself with the magnetic field. And when it does, it radiates, generates energy. And when that energy then can be detected, which can then be used to map the organs, in the patient's body. All right. So in terms of then what we have, chapter 29 is sort of like you can think of like a second part of our investigation of magnetic fields and magnetic forces. So we're going to be looking at two very important concepts, or basically the or you can say techniques and equations that we can use to solve for the magnetic field, depending on the type of source we have. So the first one is Biot-Savart law. So we're going to use the Biot-Savart law to calculate the magnetic field, but this is very similar to the Coulomb's law, where it is, one way of calculating the magnetic field, just like the Coulomb's law was the one way of calculating electric field, but it can get very messy. It can be very difficult, tedious, and calculations are a lot of times, involve um, really heavy integrations. And then we're going to talk about if some problems allow us to use the symmetry to solve the, let's say for the magnetic field, then we can apply the Ampere's law, which is analogous to the Gauss's law, allows us to use some kind of loop that will allow us to find the conditions where the magnetic field is constant and uniform, and allows us to calculate the same thing that we could do with the Biot-Savart law, but with only few steps. So kind of similar to the Coulomb's law versus Gauss's law. And here we have Biot-Savart law versus Ampere's law. Both allows us to get the magnetic field, but Ampere's law allows us to use the symmetry of the problem to get the magnetic field in much, let's say, simpler, let's say, a manner. All right. So let's look at in terms of some little of history behind the magnetic field and electricity relationship. So magnetic field and electricity, or magnetism and electricity, uh, was considered completely different branch of physics for a very long time. Um, and just like any, let's say, experiment or any type of, let's say, the concept that we have, eventually we can find a link between them. So here we were able to find a link between electricity and magnetism, and it was again done by accident, like a lot of times in experimental sciences. So here we have Hans Christian Ørsted, who was doing an experiment in his classroom when he discovered that a compass sitting on the table was deflecting every time he had a current running in his circuit. So he had basically some kind of simple circuit in his on his table where he was demonstrating that to his students. And as soon as he would have a current running to the wires, he would see the compass needle deflecting. Then let's say when he turn off his circuit, compass needle will go back to just pointing in the direction of the Earth's magnetic field. That means he discovered relationship between electricity, which is the current running through those wires, and a magnetic field, which is the compass. Remember, compass is a magnet, right? The needle of the compass is a magnet. So if there are no sources present, it always aligns itself with Earth's magnetic field. But as soon as you have another source, it then moves towards the superposition of the two sources. So that's why every time you bring compass near an electric circuit where there's a current running through wires, it will detect magnetic field. That means there is another source of magnetism, and that was current going to the wires. So current carrying wire is another source of magnetic fields. So that's kind of, you know, opened up a lot of opportunities for scientists at the time to explore. Is the, let's say the reverse is also true. But that means if we can get magnetic field from electricity, can we get electricity from magnetism? That means, if they're related like that, can we go back and forth? And obviously, the answer is yes, we can. And Faraday and Henry, which mostly going to be, we're going to see them in chapter 30, they made a lot of contribution in that particular, let's say, field where they were able to discover that you can get electricity from magnetism. And, we're going to see in chapter 30 what are the conditions for that. So magnetism can be generated from the electricity. Electricity can be generated from magnetism, and electricity and magnetism no longer can be considered as two different branches of physics. So that's why now we call it electromagnetism, because it's basically, same theory, just, two different forms of the same, let's say, concept. Now, one of the things we will see eventually is that um, magnetism is requires sort of like, let's say, specific conditions that electricity doesn't really require. Remember there, we talked about the differences between electric fields, magnetic fields, that electric field has a starting point and end point. Magnetic field always, goes around in loops. That, for example, electric field can be generated by with moving and a stationary charge, where magnetic field, technically, we're going to see that it is only generated when you're considering a moving charge. So a moving electric charge is a source of magnetic field. It could be a single charge, it could be a collection of charges, but in order for us to get a magnetic field, we need a moving electric charge. So that's why, in a way, you can think of, like, let's say that electricity is a little more fundamental in a way that it's much more universal, where the magnetism is just basically just electricity over moving charge, right? So it's an effect of a moving electric charge. Anyways, we're going to talk about all that. We're going to talk about Faraday's and Henry contribution, and then we're going to have an entire chapter on Maxwell's contribution to putting everything together. So we have this Maxwell's equation that describe everything electromagnetic phenomenon, and he was a theoretical physicist where he put everything together, and he was able to then show that you can get electric field from the magnetic field and magnetic field from the electric field, and he also showed what are the conditions in order to get those. So we're going to explore all that. So it's very exciting. I'm hoping you are also excited to learn all about those amazing facts. All right, so let's take baby steps though. Right now, this will be in terms of looking at a single moving charge. So what we have here is, so over here you can think, like, let's say that's a charge going into the page. So that's a single charge, single electric charge going into the page. And what it does, it generates those magnetic fields, which are those blue circles, around that electric charge. That means this guy here is our electric charge. So this is our electric charge. And it's going into the page. So if it's going into the page, then one thing we can do here is we can find the direction of the magnetic field it generates using a right-hand rule. So right-hand rule allows us to use another sort of, like, let's say, right-hand rule technique that deals with current or moving charge and the magnetic field generates. This right-hand rule is not for the force. Remember, there was a right-hand rule that we used in the previous chapter that was for the force. So this one over here is specifically has two quantities that you take into account. So for this, if it's just a moving charge, that means you're looking at the velocity and the magnetic field. That means we can use the velocity to find the magnetic field. So in a way, think like this. So if you have your thumb in the direction of the velocity, that means sort of like this into the page, then you can see, right, then your fingers will curve around, I don't know, like this, right? So they will curve clockwise. So try to do that, right? Your thumb into the page, and then you will see then your fingers curl clockwise. That's how we can use right hand to find the direction of the magnetic field. So this is the magnetic field that this charge generates. And this magnetic field, you can see, right, is pretty much depends on a distance from that moving charge that we were considering. Further you go from the charge, weaker the magnetic field. Generally, the magnetic field generated by a single moving electric charge is very, very small. So, but still, it's there and we can calculate that. All right, so this equation pretty much gives us the magnitude and the direction of this particular configuration. That means you have a particle moving into the page with some velocity. So let's say here I can say velocity is um, I don't know, some v for its value, right, for its magnitude, and let's say negative k hat for its direction. That's my velocity direction. And then what I have here is in this equation, this b here is the magnetic field. So the magnetic field, then you can see, right, it's proportional to q, which is the, obviously that's one requirement. There's to be electric, charge. There's to be a charged particle. Then v cross what we call r hat. R hat is, you can see, right, it's a unit vector from point charge toward where the field is measured. For example, then, let's say I want to find the field strength right here. So let's say I want to find the field strength right here. Okay. That means what I can do here is this r hat will be then right there, that unit vector over there. So unit vector from point charge toward where the field is measured, because I'm measuring the field here is that at that point P. So most of the time, one thing I can do here is, let's say over here, I can see that R hat can be replaced with I hat because, it's pointing to the right in a horizontal, direction. So I can say R hat is equals to I hat. So then I can replace, for example, this Q V cross I hat, where this becomes basically Q V negative k hat, then cross I hat. So that's what I will have. And remember, this is proportional. I'm still, talking about in terms of what is B is proportional to. Okay. That means it's a cross product. And cross product means that when I calculate, I'm going to get a direction and magnitude, both combined together. Okay, because cross product always, or a vector product, right, allows me to get the magnitude. I can simplify this equation. Remember, the cross product between two vectors can also be written as AB, which is the product of their magnitude, and sine of, let's say, angle theta between them. So that means this can also be written, so V cross R hat can also be written in terms of magnitude of the V, magnitude of the R hat, which is always 1, then sine of theta. That means becomes V sine of theta. So like in terms of, if I know then in terms of the magnitude of the velocity, right? If I have the magnitude of the velocity, I can just calculate the, let's say in this case, right, I can calculate the magnitude of the magnetic field, because at the end of the day, I can get the direction uh, for the magnetic field by using the configuration. So for example, in this In this case, magnetic field always tangent to those blue lines, right? And that means at this point, the magnetic field will be pointing like that. So this will be my magnetic field. So when I calculate, I'm going to see I'm going to get a negative j hat direction for the magnetic field. And that's what I have, right? Negative k hat cross I hat. That's pretty much going to give me negative j hat direction. All right. The idea here is, so r is also the distance from the point charge, right? From the charge, moving charge to that point of interest. Okay. So that's kind of like, let's say, what we have. Obviously, then if we go to proportionality sign to equal sign, then we introduce a constant, and that constant is magnetic constant. So mu naught over 4 pi. So you can write magnetic constant. So mu naught is the magnetic constant, but then we divide it by 4 pi. That's because mu naught itself is equals to 4 pi times 10 to the negative 7. Okay. That means if you take 4 pi times 10 to the negative 7 and divide by 4 pi, pretty much 4 pi's cancel out. But, so this is basically 4 pi times 10 to the negative 7. So I recommend always use this because this is the proportionality factor in front of it. Um, so, so using this, then we can calculate the magnetic field, both strength and the magnitude. So let's look at an example here. All right, so at the time t equals 0, a particle has a charge of 12 microcoulomb and is located at z equals 0 plane at x equals 0, y equals 2 meters. And it has a velocity equal to 30 meter per second I hat. Now, what we want to do here, we want to find the magnetic field in the z equals 0 plane for A, when basically find it at the origin, and B, finding at x equals 0, y equals 1 meter, and C, x equals 0, y equals 3 meters. That means we want to find, basically the magnetic field at those positions. That means we are changing our point P, point of interest, where we're calculating the magnetic field. But in a way, what we have here is this. So if I have this as my coordinate system, I know where the particle is. So particle, this is the position of the particle, x equals 0, y equals 2. So let's say 1, 2, right here. Let's say here's my particle. And it is moving to the right with the velocity of 30 meters per second I hat. Okay. That means, in terms of my velocity, it's a horizontal velocity. Okay. Now, what I want to do here is for part A, I want to find, okay, so what is then the magnetic field it generates at the origin? Okay, so now, obviously, because it is moving, it generates magnetic fields. And the magnetic field it generates pretty much go like this. Like that. So that's how the magnetic field pretty much, well, I could probably done a better job of that. So basically something like that, right? So that's curling around, let's say the moving charge in a YZ plane. Okay, so that's why one of the things I can do here is I can say, okay, what is the strength at that point P, which is, for part A is the origin, then point 1, which is right here, which is, let's say right here, and, point 3 somewhere right there. Okay, so let's kind of get rid of that. So think like this. So these are my points. So if this is my coordinate system, okay. So let's take that to be the origin. So this is the origin. Then this is x equals 1. This is, sorry, y equals 1, y equals 2. And here's y equals 3. That means I have those as a point of interest. So first I'm going to take origin as a point of interest. I'm going to say, here's my point of interest. Okay. So that means, the r hat vector is going to be like this. Okay. So then I can say, all right, so then for part A, my r hat is negative j hat. My r here is 2 meters because it's position from the position to the origin, right? It's just 2 meters. So those are the two things that I want. So I'm going to then say, all right, so magnetic field is equals to mu naught over 4 pi then Q times V cross B. Okay. We're given that Q is 12 microcoulomb. So Q V cross, sorry, V cross R hat, then divide by R square. Okay. So we start with this equation. Okay. Then I'm going to say, all right, so this is then equals to mu naught over 4 pi times Q. And then for V, I'm going to write it in terms of, let's say, Vx I hat, because this is the horizontal component, right? So it has only horizontal. So Vx I hat cross R hat. And R hat here is negative J hat. Okay. And then divided by, R square. That means, in terms of what we have here is, so like, let's say, I can say that this is just mu naught times Q over 4 pi, then Vx, then I hat cross negative J hat. That will give me basically a K hat as a direction. Okay. Which in a way you can think of like this, right? So here's one way to, kind of like get that cross product. So what you have here, you have I hat and you have negative J hat. Okay, so I hat and negative J hat. So what we're going to do here is we're going to use our hat. Let's see. All right, so if I'm using my right hand, I can use my right hand rule to figure out what is I hat cross negative J hat. Okay. So one thing I can do here is I can have my, fingers in the direction of I hat, but then I'm going to need to be able to curl my fingers in the direction of negative J hat. So in order for me to be able to curl, then my thumb should be pointing there. Okay. So that means, what I have here is I have to, have my fingers in the direction of, positive I hat direction, then be able to curl in the direction of negative J hat direction, and my thumb is pointing into the page. So my thumb is then pointing into the page, which is right here. That means this is going to give me negative. So I'm kind of put it here. So it's going to be negative K direction. So mu naught Q Vx, and the direction is negative K hat. That's the direction that I get from here. All right, so then we are ready to calculate. So mu naught is 4 pi times 10 to the negative 7. Divided by 4 pi. Then Q, which is 12 times 10 to the negative 6 Coulomb. Then V, which is 30 meters per second. Then divided by R square, which is just 2 meters square. Then negative K hat. If I calculate this, I should get the negative 9. Negative 9 picotesla in a, this negative already gives me the direction, that's the direction over here that's moved in front. So K hat. That means I got magnitude and direction. So it's negative 9 picotesla pointing into the negative Z direction. As you can see, right, it's a very small magnetic field. Pico is 10 to the negative 12 because that's just just a single charge. Magnetic field that they generate is extremely tiny, but we can obviously calculate that. All right, so for part B, in a way, the only thing changes is this. So my R hat is still negative J hat because now this is my point, point of interest. So that's my point of interest. The only thing here is that R is equal to now 1 meters because particle is at y equals 2 meters. Point of interest is y equals 1 meter. So R is just 1 meter. Okay, everything else is basically the same. So that means even in terms of the direction, right, I get everything still the same. So B is equals to mu naught over 4 pi Q. So still have Vx I hat cross negative J hat divided by R square. So the only thing exactly changing is, I say, right, this R over here for this part B. So I can calculate this, and you can see, right, this is actually closer to the particle, so you should expect a stronger magnetic field. So we get negative 36 picotesla in a, k hat direction, negative k hat direction. So it is, right, it is, much stronger magnetic field compared to, when it was 2 meters, like when it was at the origin. For part C, then, what we have is point of interest now shifts upward. So the R hat is now pointing in this direction. So that's my R hat. That means for part C, the change here is R hat is equal to now J hat. My R is equals to still 1 meter because it's only 1 meter above where the particle is. So still Q is equal to 2 microcoulomb, and V here is still 30 meter per second I hat. So then here, if I calculate the magnetic field, it will be mu naught Q over 4 pi, then V cross, in this case, what I get here is I get then Vx I hat cross then J hat divided by R square. And one of the things we will see here is if I'm doing I hat cross J hat, I get K hat rather than negative K hat that I got previously. That means I'm going to get pretty much the same answer because everything is the same except this cross product, but that's a cross product of the unit vector, so it just changes the direction. So then I get 36 picotesla, but in this case in the K hat direction. Okay. Because you can see, right? So it's coming out, going in, coming out, going in. So like, let's say here's out, here's in, because it goes, in a circle, right, around the moving charge. Okay, so this is how we can find that magnetic field, different positions from a moving charge. Here's one more example. Here's just basically a little bit of different, approach that we can see. So you have a point charge particle that has a charge Q equals 4.5 microcoulomb, is moving with a velocity of 3 meter per second I hat, right? Along the line Y equals 3 meters in the Z equals 0 plane. Okay, so very similar, very similar problem. Find the magnetic field at the origin produced by this charge when the charge is at the X equals negative 4 meters and Y equals 3 meters. Okay. So that means one thing I have here is this. Okay. So we still have a charged particle. So Q is equals to 4.5 microcoulomb. So we have a charged particle. And we have a coordinate system, right? So let's say right now my point of interest here is the origin. Okay. Okay. Now, what I'm going to do here is I'm going to draw a vector R. So you can see, right, this is the vector R from the particle to the point of interest, point P. That's not the R hat vector, it's a vector R, which is different from a R hat vector. Unit vector R hat is right here. That's my R hat vector. But this is vector R. But they are related in a way that, for example, R hat, which is a unit vector, is equals to the vector R divided by the magnitude of vector R. Okay, so vector R divided by magnitude of vector R. But here's what I have. So you can see that vector R is from here to there. So I can see that it has a length of negative 4 in the X direction and positive 3 in a Y direction, but technically, sorry, actually not true. So since it's pointing like that, so if I break it into things like this, so this is this vector R. If I break it into components, then components are this. So this is, Rx, and then this is Ry, okay, which we can see is basically negative. That means vector R is equals to Rx I hat minus Ry j hat. And we even have those values, right? So it is 4 I hat minus 3 j hat. Okay. 4 I hat, in terms of they're in terms of meters, right? So we're giving them in terms of meters, but let's say 4 meters I hat minus 3 meters j hat. as you can see, right? Again, if I take that, right, if I break this down into components, you're going to see that, the y component of this r is pointing down, so it's negative, x component pointing to the right. Okay, so that's what I have. That's my vector r in terms of its components. Now I can also calculate its magnitude. So its magnitude will be just basically 4 square plus 3 square, right? 4 square plus 3 square, which will give me 5 meters. So that means, I cannot represent r hat as a I hat or j hat or k hat. So I need to first find how to represent r hat. So that's why right now I have r hat as equals to, so what I have here is vector r divided by magnitude of vector r. Vector r is 4 I hat minus 3 j hat, and this is divided by 5 meters. Okay, so that's basically what I have. And if I then calculate this, right, that means 4 over 5 I hat, I get 0.8 meters I hat. 3 over 5 j hat gives me 0.6 j hat. That means my vector r hat can be calculated using this. And that's what I have. That means in this equation, right, where I have magnetic field, I have mu naught over 4 pi, then times qv cross r hat. If the r hat cannot be simply in a direction, horizontal, vertical, or in a z direction, I have to use this to find the direction of the r hat. All right, so that's why I showed you sort of like, let's say, this example so you can see how to approach a problem like that. Okay, but still, other than this, once you calculate r hat, it's pretty much same thing. Okay, so what I have here is this will be mu naught q over 4 pi. Then v, remember v here is in terms of its magnitude, right? It's horizontal again. Okay, so vx I hat cross, then for the r hat, then I'm going to put 0.8 I hat minus 0.6 j hat. And this is divided by the magnitude, which is, 5 square. So it's pretty much 25 meters square. Okay, well, calculating this, what I'm going to get here is if I plug in the values, so 4 pi times 10 to the negative 7, and units are Tesla times meters per amps for the mu naught, divided by 4 pi. Then the charged particle is 4.5 times 10 to the negative 6 Coulomb. Okay. Then 3 meters per second for the velocity, or that's the speed at this point. Okay. Then what I have here is this. So if I kind of look at this portion over here, where I have the cross product. See, what I have here is there's a cross product. So I had cross. So I have 0.8 I hat minus 0.6 j hat. Okay. That means first, what I'm doing here is I'm crossing those two. Okay. So that becomes 0.8 I hat cross I hat. Then crossing those two. Then minus 0.6 I hat cross j hat. Okay. Now, if I look at this, I can see that's a cross product between two unit vectors that point in the same direction. This is going to give me 0. So then this becomes negative 0.6 I hat cross j hat. You can see, right, I hat cross j hat. Have your fingers in the direction of I hat, which is to the right. Then curl your fingers in the direction of j hat, which is up. You will see your thumb is pointing out. So that means it's k hat. That means what we get from here is 0.6 negative k hat. Okay, and then this is divided by 25 meters square. Now, if I then use this calculation, right, plug in everything and calculate, so we'll get negative 3.2, and negative is the direction of the k hat, right, times 10 to the negative 14 Tesla in the negative k hat direction. So basically, so that's the magnitude and the direction of the moving charge. As you can see, right, it's also very, very tiny, right? It's you know was it like a 320 picotesla? So it's again very tiny magnetic field because still it's just one tiny moving particle. But we can calculate it's non-zero and it generates magnetic field as long as it's moving. You can see, right, once it's stopped or once it starts, let's say moving in a region where there could be a magnetic field canceling something like that, right? So at this point, one of the things we can see here is this particle will be generating its own magnetic field. So this is not the external magnetic field. This is the magnetic field that this particle generates because of its moving. So any type of motion, let's say for the charged particle, translational, rotational, vibrational, can be used to generate magnetic field. All right, so next we're going to look at in terms of current as a current in a wire as a source for the magnetic field rather than just a moving charge. So we're going to investigate magnetic field due to, a wire that has a current running. Remember, what is a current? It's just a collection of particles now moving. That means it's not just one particle moving and generating magnetic field, but a bunch of particles moving and generating magnetic field. So that's why magnetic field generally is stronger because of the wire, has, you remember from previous chapters, right? Very large amount of particles moving in the wire. So then you can think of, like, let's say if there's a current running through this wire, then at some point of interest, I can calculate the magnetic field because magnetic field will be due to all the, let's say particles that are moving inside the conductor combined. So this magnetic field will be generally, since, it's a very large number, calculation can be tedious. What we're going to do here, we're going to look at some kind of small element, infinitesimally small element of current, and then use that to find the expression, and then to integrate, then to find the magnetic field from all of the charges combined. Okay, but very similar to the calculation of electric field due to the uniform, let's say, uniform configurations. When their charges are uniformly distributed along the, a plane or a line or a sphere or something like that, remember? So we would choose like a small element, use that to find the expression, and then, integrate to find the total effect. So that's kind of what we're going to be doing here. That means if you have a wire where there's a current running through that, so we're going to choose a small element of that current that has a length ds. And once we do that, we can then choose a point of interest. In this case, let's say this point P over here. Then we draw a line, distance r from that, and then we have our r hat vector, which is always from your unit element, from your small element toward the point of interest. And then we can set up an equation, which is, you can write dB out, which is the dB is the magnetic field generated by this small element. Okay. Once we find the expression, then we can integrate, let's say, from one end to other, or from negative infinity to positive infinity, depending on what type of wire we have. But that's kind of what we have. So again, think like this. Suppose the current distribution is a wire carrying steady current I. And if we have that, we can then experimentally determine the magnetic field strength. And these are some of the experimental results. So let's say, so vector dB is perpendicular to both ds, which is the length element. Let me think like this. So if this is my wire, so if I choose a small element, right? So if I choose a small element, so let's say the current here is going like this. Okay. So if I choose a small element, that small element will be, let's say, in this direction, right? So this is my ds. Okay. So let's say I want to find what is the magnetic field at this point P. So I draw a line. Basically this is r, the distance from the point of interest to my element. And then this will be then the unit vector, r hat. Okay. So what you can see here is this magnetic field will be perpendicular to both ds, which is, this is a vector, right? Oops. Sorry, guys. So this is the vector ds and the unit vector. Now, what I have is this. My ds is technically can be considered as ds I hat. Our r hat unit vector technically can be considered, some kind of, I hat and j hat, right? Combination of I hat and j hat. That means in order for this magnetic field to be perpendicular to both of them, that means it have to be out of the page or into the page. Okay, and that's what we're going to see when we actually calculate those, examples, right? The magnetic field in those examples, we will see that magnetic field is indeed perpendicular. So in this case, it's either going to be into the page or out of the page, and it cannot be, one or the other. Well, it depends on the current, for example, depend on the current and the, direction of the ds and the direction of the r hat. So in this particular case, for example, the magnetic field will be out of the page. And the easiest way to get that is you have your thumb in the direction of the current, and then you will see that your fingers will then be curling, out of the page, right? So thumb in the direction of the current, your fingers will be curling out of the page like this, right? That means the magnetic field at that point P will be out of the page. For example, if my point P was here, then in order for me to have my thumb pointing in the direction of the current, my fingers then would have been, curling like this, which means like they will be curling into the page, right? So they will be curling into the page. And that would have been giving me magnetic field out of the page, sorry, into the page. And then here, magnetic field out of the page. Okay, so those are the, some of the things we will see. All right, so that means magnetic field will be perpendicular to both length ds element, right, and the r hat vector. The magnitude of the magnetic field is inversely proportional to the distance r square. That means, further you are from that wire, weaker the magnetic field, just 1 over r squared, just like electric field, remember? Where r is the distance from the element to P. The magnitude dB is proportional to the current I and to the length ds of the element. That means in equation, when we derive the equation, it will be proportional to ds and then, and then the current. Okay, IDS. That means it will be proportional to the product of IDS. And the magnitude of the dB is proportional to sine of theta, where theta is the angle between ds and r hat. And that also should be obvious because one of the things we have here is we're going to have a cross product between ds and r hat. And if that's the case, then remember the cross product between two vectors is their product of their magnitude times sine of theta. So that's why there's a proportionality to also a sine of theta, because there's going to be a cross product. All right, so again, those are the different experimental results, which will allow us to get then the expression for the magnetic field due to this current carrying wire. And that expression here is given like this: dB is equals to mu naught over 4 pi current times then ds, that small element, length element, times across r hat and divide by r squared. Now, the reason we're not doing current, in a part of like a cross product is because current is a scalar quantity. We can't use a cross product with a scalar quantity. So that's why we choose a small element in the direction of the current, right? The length element. So this guy has a units of meters. So, and that pretty much allows us to calculate some kind of, cross product, because this is a vector, length is a vector, right? R hat is a vector. It's a unitless, but it's a vector. And those two, right, will always give us that cross product is how we get the direction of the magnetic field. Okay. All right, so mu naught here is, again, that's the magnetic field constant, is 4 pi times 10 to the negative 7 Tesla times meters per amps. Okay, that's basically in terms of proportionality constant, which generally also takes care of the units. So that's why. So if this is meters and this is meter square, this will cancel that, and then that meter over here will cancel this meters, and we then 1 over amps cancels the amps over here, and all the meters and amps and everything cancel out, and the only thing that survives is the Tesla, which is the units of magnetic field. All right, guys. So again, this is known as a Biot-Savart law. So Biot-Savart law gives you the magnitude and the direction of the magnetic field due to either a moving source, depending if it's a moving charge or a moving collection of charges, which is current. Okay, so generally, as I said, right. So the mu naught is known as a magnetic field constant, but there's a permeability of free space. Okay, so it's you can say it equals 4 pi times km, and km is just basically a magnetic constant. The idea here is you can calculate this, right? 4 pi times 10 to the negative 7. I think if I'm not mistaken, is I get 1.28 times 10 to the negative 7, I think negative 6. But the idea here is, most of the time you can just leave it like this because, the 4 pi's can cancel out. And then you have much simpler, let's say, calculation using this constant. Okay. So again, the Biot-Savart law gives the magnetic field only for a small length of a conductor. And then we need to integrate both sides in order to get then the contribution from everything inside your system. All right, so in this case, again, so like let's say to summarize in terms of what we have, that's because this is probably one of the hardest, let's say type of calculation we're going to see. So again, if you're given this, right, consider equation for the electric field due to the point charge, kind of comparing. So remember, this is the equation, right? K, Q over R square, R hat. And then you can see, right, electric field directly proportional to the charge, which generate electric field, inversely proportional to the distance square, and there's a proportionality constant K. Well, same way we have a magnetic field, right? So this dB is then equals to, right, mu naught over 4 pi, which is kind of like equivalent to this constant. Then I, which is the source, but we need to have a vector, so that's why we do ds cross r hat. So we need to get the direction out of that as well. So we get that. So direction of electric field is much more simpler. Direction of the magnetic field, not so much. So that's why it's a cross product, but it's also inversely proportional to distance square. So the magnitude of magnetic and electric fields vary as inverse square of distance from source. So the direction of fields different in such that electric field created by a point charge is radial, where magnetic field created by a current element is always perpendicular to both element and unit vector r. So that's why if you have a charge, electric field is simple. It's radial always from the charge. You have all the directions. Magnetic field, it is always perpendicular to the direction of the length element and unit vector. Okay, so that's why, right? If a conductor lies in a plane of a screen, dB point out of the screen at point P and into the screen at point P prime, just like I showed you in the previous slide. Okay. Also note that dB, right, this magnetic field element created at the point by a current in only small length element ds of a conductor. That's why we need to, integrate, right, to find the total, of total magnetic field created at some point P. We need to some contribution from all current elements that make up the current. So basically evaluate this magnetic, field, evaluate this integral. Most of the time those can come out. That's just a constant, mu naught I over 4 pi. Just as you take it out of the integral, and then you have ds cross r hat over r square. So that's what you most of the time evaluate. So it can go from simple to very, very tedious, depending on what type of problem you have. So you can say integral taking over the entire current distribution. So you can have either finite or infinitely long wire. You can have a straight wire. You can have a curved wire. You can have a wire loop, right? So like a ring, depending on sort of like what you have. Okay. So and the hard part is basically when you're talking about the cross product inside the integral. So that's when you have to take care of all the direction, all the magnitude, and everything of those quantities over there in order to get the right answer at the end. So we're going to do a few examples where you guys can see that. Okay. Again, in terms of then for this Biot-Savart law, right? So it's valid for current consisting of charges flowing through space. Okay. So that means every time you have a current, you can then assume that there's, they will generate a magnetic field. Okay. So ds represents the length of small segment of space in which charges flow. So Biot-Savart law gives magnetic field of isolated current element at some point. Such an isolated current element cannot exist the way isolated electric charge can. Okay. So remember, the difference here is you can have an electric field even if the charge is stationary, but you cannot have magnetic field unless the charge is moving. And that's one of the important things that we have, right? So for us, the current itself defined as the flow of charges. So that's why in order for you to have a magnetic field, you need to have a current. And that's kind of like the biggest difference between those. So let's look at a few examples over here. So we start with a straight wire that has a current 10 amp, let's say flowing from left to right in this case. So we're going to choose 4 different points of interest, A, B, C, and D. Okay. And then we're going to look at in terms of, you can see, right? So the ABCD is a rectangle with a point D in the middle of 1.1 millimeter segment of wire and point C in the wire. So we're going to find the magnitude and the direction of the magnetic field due to these segments at point A, B, and C. That means what is magnetic field at point A? What is magnetic field at point B? And what is magnetic field at point C? Where D is a point where we have our length element. And our length element is 1.1 millimeter long segment. Okay. And we have a 10 amp current, and we also given the sort of like, let's say the 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 length and the width of that rectangle. That means in a way we're given the distance between A and B, between B and C, which will then allow us to find, let's say if this is my point of interest P, then I can find this R, which is a distance from my element to that point of interest. And when this is the point of interest, then this will be my R, right? So this is RA, this is RB, and then this will be RC. Okay, that means the distance from my element to the 3 different points of interest. Okay, so let's look at the first one, A. So that's part A. And what we have here is we are looking at point of interest to be A, so PA. Now, for here, we can see that R, which is the distance, is 0.05 meters, 5 centimeters, right, from D to A. That's the distance. R hat is a unit vector, remember, pointing in a direction. So this is my R hat from the element to the point of interest. In this case, just J hat, right? And then I can, since I'm already given the current value and I'm given, let's say, the segment length, I can say then dB is equals to mu naught over 4 pi times I times then ds cross R hat over R square. Okay. All right. So what I had here is this. So in terms of my ds, and put it like this first. So you can see, right, ds as a vector is equals to ds times I hat, because I can take the length to be ds length to be 1.1 millimeter and direction is pointing R hat. So that's my ds. Okay. So here you can do 2 different things. You can use then the vector product, where you can say ds cross R hat becomes ds I hat cross, where R hat is J hat, which they'll give you ds I hat cross J hat will give you K hat. Okay. That means that this cross product ds cross R hat end up being just a ds K hat. Or you can say it's ds times, so that's the magnitude of ds times magnitude of the r hat, which is 1, then times sine of angle theta between them. And but again, because one is horizontal, the other one is vertical, then this becomes just basically ds, because sine of theta is equals to 1. So if you use this method, then this doesn't give you the direction right away. So you have to use then the right hand rule to get the direction, where the direction will be like this, right? So your thumb will be pointing in the direction of the, ds, and then where the point of interest here, if your fingers curling outward like that, right? Then that means magnetic field will be out of the page, so in a positive k hat direction. And that's what we have, right, in this case. That means, either ways will be correct. So let's use the, let's say in this particular case, this method over here, because right away gives you the direction. But obviously, always this is another way to go. And sometimes when specifically r hat is not constant, and like let's say not one of those r I hat, j hat, k hat direction, you can either use the technique that I showed you, where we can use r hat as a vector r over the magnitude, or just find that if you can easily find the angle theta between ds and r hat, you can use then this second method. Okay, so let's see what we have. So part A, dB is equals to, so mu naught is 4 pi times 10 to the negative 7 divided by 4 pi. Current is 10 amps. And then using this first method, ds is 1.1 times 10 to the negative 3 meters, because it's in millimeters, divided by the distance, which is 0.05 meters squared. Okay, calculating this, we should get 4.4 times 10 to the negative 7 Tesla in a k hat direction, because there was a, remember there was a k hat right away with this value, so you can get that magnitude and the direction. All right, so that's for the finding, the direction and magnitude of the magnetic field and direction at point A. So now let's look at point B, which is another point of interest. So here, this is my r, and this is my r hat vector, and let's say this is my ds vector. Okay, again, ds is equal to ds I hat as a vector, and what I have here is I can find r from using the Pythagorean theorem. So it's 0.05 meters square plus 0.14 meters square. I can use that to calculate r, um, which then can be used in our calculations, right? Let's say here, and I can then use those two to get then angle theta as well. So I can say then the theta is equals to inverse tangent of 0.05 over 0.14. So we get 19.65 degrees. Then for part B, I can calculate dB from this. So I can say this is equals to 4 pi times 10 to the negative 7, or 4 pi, 10 amps, then magnitude. So here I'm going to use the second method, where I'm going to say magnitude of the first vector times magnitude of the second vector times sine of angle theta between them. So this will be then magnitude of the ds will be just 1.1 times 10 to the negative 3 meters. Magnitude of the r hat is 1, then sine of 19.65, which is the angle between them, divided by then r square, which will be 0.05 square plus 0.14 square. Okay, so since it's r square, I technically I don't need the square root, right? I can just do this. Okay, so calculating this, I will get 1.67 times 10 to the negative 8 Tesla. The only thing here is, I don't get the direction right away. If I use this method, I would have gotten direction right away. Here, I don't get the direction, but I can, use the right-hand rule, right, where I can see anywhere above this wire, the magnetic field is coming out of the page. So it will be in a k-hat direction. Okay, so that's part B, which is, finding the magnetic field at point B. Okay. The last one is, what is the magnetic field at point C? So let's kind of go back like this. So again, what I have is that dB for C is equals to mu naught I divided by 4 pi. Then I have ds cross r hat divided by rc, like that, squared. What I have here is, this will be my ds, and now this will be my r, and then this will be then my r hat. And then what I can see is that this is basically my r hat is I hat, my ds is also I hat, and when I do a cross product of two I hats, it will give me 0. Okay, that means this whole thing is 0. That means there's no magnetic field on the wire itself, which should make sense, right? If the magnetic field is generated by the wire, it generates magnetic field around the wire, not on the wire. So anywhere on the wire, there is no magnetic field generated by this wire. There could be some external magnetic field, on the wire, but not from the magnetic field it generates. All right, so let's look at then next example. Here what I have is magnetic field of a straight current carrying conductor. Okay, so what we're gonna do here is, imagine you have a finite conductor. So let's say if you put it at the origin, it goes from plus a to minus a on each side. That means it has a length of 2a. Okay, and it's centered at the at the origin, and we want to find the magnetic field at point P over here, some distance x along the x-axis. So one of the things what I have here is, so let's say this will be then, if the current is up, right? So you can see, right, there's a upward current. So then this will be my DL or DS, pretty much the same thing. So then this will be then the angle, right, phi between those two vectors. So what I can do here is, so let's say call this some angle theta, if you want. So this will be some angle theta. And then I can find then the magnetic field at that point P. Okay, so using the right-hand rule, right away I can see that if my thumb is pointing in the direction of the current, so then to the right of this wire, my fingers will curl into the page. Okay, I hope I have enough, fingers, like 5 fingers, not like 6 or 7. All right, so let's say if you have your thumb in the direction of the current, then your fingers curl into the page to the right of it. That means there will be magnetic field everywhere here into the page, but the difference field will be different strength, right? Because different distance from the wire, but they're all going to have exactly same direction into the page. Now, let's say if I'm choosing that particular element, dl, then I can see, right, this is my r, which is the distance from there. So then I can kind of like find that expression. So dB is equals to, so the general equation, right, mu naught over 4 pi, and I d, again, you can use dl cross r hat over r square. Now, what I have here is, you can see, right, in terms of my equations, kind of similar in terms of that my dl is a small element. And in this case, I can say that my dl as a vector is dl j hat. Okay. But my r hat is not, I hat or j hat, right? It's not one of those unit vectors. So we can technically, do several things, right? We can use this to find in terms of, r hat, or sorry, vector r over r, or I can simply just write it like this. So it's mu naught over 4 pi, then I dl, then which is the magnitude, right? So magnitude of dl, magnitude of the r hat is 1, and then sine of angle theta between them, and then this is divided by r square. So I can basically write it in terms of this. All right, so but from here, what we're gonna do is we're gonna, this is the current I. Okay, so from here we're gonna then see that R is square root of x squared plus y squared, and if I'm using this angle here as a theta, then sine of theta. So then I can say that, see, this is I have a triangle like this, where if this is my theta, this is x and this is a, then tangent of theta becomes basically x over a. Okay, so that means I can do some substitutions, right? Same way, then sine of theta is equals to opposite over hypotenuse, so becomes x over r. Okay, so let's find then the, sort of like the expression. So let's go to the next page, next slide, and start writing down those expressions. So in terms of what I have here is this, right? So dB is equals to mu naught I over 4 pi. Then dl, remember, um, so dl, I can write it in terms of basically dy, right? Because it's along the y-axis. So I can say just some dy. Okay. So dy, and then sine of theta divided by r squared, which I can write it in terms of x squared plus y squared. So that's my r squared. Okay. Then, sorry, that's not y, but a squared, because that's, this distance we just take to be a. It's along the y-axis, but it's, it's still, given in terms of a. Okay. So from here, I need to then, so like simplify my equation, because theta, y, and r, pretty much are not independent of each other. So what we do here is we write down in terms of, what those quantities are, right? In terms of, like, let's say, as I said, right? So tangent of theta is equals to x over, in this case, right? So x over y, for example, and r is equals to x over sine of theta, which can be written as, x over cosecant theta. Okay. From here, I can see that y is equals to, so if tangent of theta is x over y, because remember, so if I'm taking this to be my theta, x is the opposite, and y is technically, so like, let's say, is that, and thing like this. So what I have here, this is y, right, where my element is. So that's basically my adjacent side. So then y is equals to x over tangent of theta. Okay. So then 1 over tangent theta is cotangent x, x equal cotangent theta. Then what I do here is, see over there, I have dy. So I can then take dy and take the derivative of that with respect to theta. So dy d theta becomes then negative x cosecant squared theta. So that means dy is equals to negative x cosecant squared theta d theta. Okay. So that's my, in terms of what I have for dy. Okay. Also for the sine of theta, right? So in this case, for sine of theta, I have, I don't know if I've written this. So this is opposite over hypotenuse. So it will be x over x squared plus y squared 3/2. Okay. That means if I go here and continue, then I can say dB is equals to mu naught I over 4 pi. Then for, so what I have then is just basically dy. So sine of theta, so dy over, for example, x squared plus a squared. Then so actually here for sine theta, I'm going to have to write a instead of y because, I'm talking about the whole thing. So here is, for sine theta is replaced with x over x squared plus a squared 3/2. So I end up with dB is equals to mu naught I over 4 pi. Then x dy over x squared plus a squared 3/2. Okay, so that's my expression. So that's expression for this small element at that point P, and I can calculate what will be the value for that. But then if I want to find the whole thing, then I need to obviously integrate. So integrating both sides, since this is just nothing but the constant. So the left side is just then the B, then equals to mu naught I over 4 pi. Then whatever I have here is this, right? X dy over x squared plus a squared 3/2. All right, so then this is basically where we can, start using some of those substitutions. So this is, not something that we can simply integrate. This requires either one of those, using one of those, integral tables, or, at this point, I expect you guys to be able to, find this, like let's say right substitution, right, and do the integral. All right, so what we do from here is basically this. We pretty much go and, so here we say, let's see. Sorry guys, I made a mistake here. This, I don't know why I replaced this with, so this should be Y everywhere. I replaced it with A by mistake. Okay, so let's call it Y over there. I think I have it everywhere. So saying Y is equals to, okay, so Y is equals to, from here we can see, right, tangent of theta is X over Y. So Y is then X over tangent of theta, or X times cotangent of theta. Okay. Then dy is equals to, so if you take it like in terms of dy d theta, so like what did we did over here, right? So it's negative X cosecant squared theta. Okay. And what I can do here is to make a substitution. B is equals to mu naught I over 4 pi, an integral. So X, and for dy, I replace negative X cosecant squared theta. So there's d theta over there, d theta, divided by x squared plus y squared. So here I do x squared plus, so then for y is I put x cotangent theta. So x cotangent of theta squared 3/2. Okay. So this is then equals to mu naught I over 4 pi, then integral. So then I get negative x squared cosecant squared theta d theta over. So then I get x squared plus x squared cotangent squared theta 3/2, which then I can simplify into negative x squared cosecant squared theta d theta. So here the x squared I can factor out and take it out of the parentheses. So this becomes then, because it's x squared times 3/2, this becomes x cubed. then 1 plus cotangent squared theta, 3 halves. So from here, I can cancel x squared here and cube over there. So then this becomes mu naught I over 4 pi, an integral. So negative cosecant squared theta d theta over x. And what I have is that I have 1 plus cotangent squared theta. So 1 plus cotangent squared theta gives me cosecant square. So cosecant square to the 3 halves then gives me cosecant cube theta. Okay. That means from here, what I get is mu naught I over 4 pi integral. So this goes away with that. So I have 1 over cosecant square, 1 over cosecant theta, and 1 over cosecant is then basically a sine. So it becomes negative sine of theta d theta over x, which x in this point is nothing but a constant. So it can come out. So then becomes mu naught I over 4 pi x, then integral going from negative a to a. Well, actually, this is, since we're now doing in terms of the theta, becomes negative theta 1. So let's say to plus theta 2, which is going from here to all the way there. That means we are integrating the whole thing. So let's say this is negative theta 1. This is positive theta 2. So basically doing that. Then sine of theta and d theta. So let's not forget the negative. So that's because what I'm going to do here is when I get this integral, then I have, like, let's say, sine theta d theta. So I'm going to get then negative cosine theta, and that's going to cancel out the negative. So, but what I will get here is I'm going to get, let's go to the next page. So from that, I should be able to get, the sine of cosine of theta 2 minus cosine of theta 1. Sorry, cosine of theta 2 minus cosine of theta 1. And then from here, that negative going to make that, that negative going to go into the equation and make that as a positive. All right, so the idea here is magnetic field. So we basically will be equals to, sorry about that, guys. So mu naught I over 4 pi, then cosine of theta 2 plus cosine of theta 1. Okay. All right, so then another version of that can also be written like that in terms of the, 2a x squared plus 2a. So since the direction of the magnetic field from all parts of the wire is the same, we can integrate, right? And the magnitude of the magnetic field and obtain this result. Okay. All right, so from here we can get several things. Let's say if it's finite or infinite wire. So for example, this is pretty much for the finite wire that has, length, a plus 2a, right? But if the length of the wire is very large compared to the position, so for example, think like, so this was wire and this was the position P. That means this length L was comparable to the point of interest. But if the wire becomes so large that point of interest is basically becomes, negligible compared to the, let's say, the length of the wire, so we can say that it's infinitely large. That means, the length of the wire is so much longer than the point of interest that we're considering. So we can take this limit where x is much, much less than a. And if that's the case, then this equation can be simplified to B is equals to mu naught I over 2 pi x So becomes 2a over, so here this can be, because this is sum, in this sum this is basically pretty much becomes negligible, so this becomes just square root of a square, which then will give you, you know, just a, sorry, this was 4 pi over there. Okay, so 2a over a, and the a's cancel out, so you have mu naught I times 2 over 2 pi x. Here this cancels out, so you have then 2, so magnetic field is equals to mu naught I over 2 pi x. That means the point of interest is on the x-axis. Okay, but if the point of interest on some, you know, different position rather than x-axis, then it can be kind of like simplified to that, because you can have a horizontal wire and point of interest here. That means, you know, what we're doing here is r is the position of the point of interest relative to the infinitely long wire. So if the magnetic field near a long straight current carrying conductor can be then simplified to constant mu naught times the current divided by 2 pi times the distance from a conductor. So simplified to just this equation. All right. So in terms of then, as I showed you, right, the right-hand rule, we can always assume that this second right-hand rule can allow you to find the direction of the magnetic field. And magnetic field always curls around the wire, as you can see, right? In this case, your thumb is direction of the current, and then your fingers curl in the direction of the magnetic field. So you can see, right, if the current is up, magnetic field is counterclockwise. If the current goes down, magnetic field will be then counterclockwise. It will, sorry, here is counterclockwise. If the current is down, the magnetic field will be clockwise. So it changes the direction depending on which direction is the current. Magnetic field strength will not change, but the direction of the magnetic field will change. Okay. All right, so let's look at this example over here. So two long straight wires, one above the other, are separated by a distance 2a and are parallel to the x-axis. Let the plus y-axis be in the plane of the wires in the direction from the lower wire to the upper wire. Each wire carries current I in the positive x direction. What are the magnitude and direction of the net magnetic field of the two wires at the point in the plane of the wires at three different positions? So we're given midway between them, a distance a above the upper wire, or distance a below the lower wire. That means what we're doing here, we're calculating the magnetic field due to basically two wires parallel to one another. Okay, so let's say, let me do that diagram here. So imagine here's one wire and here's the second wire. So both have a direction of the current. So this is I1, this is I2. And they are separated by a distance of 2a. That means this is 2a. Okay. Now, what I have here is this. So let's concentrate on the wire 1. All right, so let's talk about, for part A, uh, for the point of interest to be midway between those two wires. So let's say somewhere right here, this is point P, which means it has distance A from wire 1 and distance A from wire 2. Now the question here is there a magnetic field there at that point P due to wire 1 and then due to wire 2? And if there are more than one, can we calculate the net magnetic field? So let's start with wire 1. Wire 1 has current to the right. And again, if we use the right-hand rule, we can see, let's use this color for the magnetic field due to wire 1. So we can see that anywhere below wire 1, the magnetic field, let's say again, so if you have your thumb in the direction of um, the current, then you can see your fingers will curl like this, right? So like, let's say, curl into the page. Didn't work out that well, but so look at this. So curl into the page for the wire 1. That means magnetic field 1, let's call it magnetic field 1, will be into the page like this, everywhere below this wire 1. That means this entire region, including everywhere below, will be like this. This is magnetic field B in due to the 1. So this is let's just call it B1. Now, if I then continue curling my fingers, and I can see that above wire 1, the magnetic field 1 will actually be coming out of the page. That means this will be magnetic field 1 everywhere above the wire 1. So this is B1 again. There you go. So that means magnetic field 1 is into the page below wire 1 and out of the page above wire 1. Same way we can see that if I'm using the magnetic field due to wire 2, it's a different color for that. Okay. So for that, again, same thing. If I use same, my thumb in the direction of current 2, and then if I curl below wire 2, the magnetic field will be into the page. So this will be magnetic field 2. This is B2. And everywhere above wire 2, magnetic field will be out of the page. Basically something like this. Okay. So that means what we get here is this. For point, let's call this point 1, since this is basically part A, so this is going to be point 1. For point 1, then, okay, I have magnetic field 1 that is going to be into the page. That means magnetic field 1 is equals B1. Sorry guys, having difficulty writing on the screen for some reason. So B1 negative K hat. Okay. And then magnetic field 2 will also be present at point P1, but in this, you can see right for this magnetic field 2, it's going to be out of the page. That means this is going to be then B2 plus K hat. Okay. So, which means the net magnetic field is magnetic field 1 negative K hat plus magnetic field 2 positive K hat, and that will be, the sum, right? And because both of them are, along the same axis, K, we can think of like, let's say it's just algebraic sum. So this means equals to, now, since it's a straight wire, current carrying very long straight wire, then magnetic field will be given as mu naught I1 over 2 pi A negative K hat plus mu naught I2 over 2 pi A, because both of them have distance A from it, and then we have current 1 and current 2. One thing we have here is we were told in the problem that both have the same current. So if both have the same current, have same distance from the point P, but opposite directions, that means you can see, right, their sum will give us 0. That means strength of the magnetic field for B1 and B2 at that point P, exactly halfway between them, they both have the same strength but opposite direction, so they add up to 0. For part B, we're asked to find some point A below the wire 2. So let's say here's our point P2, point of interest. Okay. Which means that I can see that the way I have magnetic fields, both magnetic field B1 and B2 are into the page. That means the net magnetic field is equals to B1 negative K hat plus B2 negative K hat. So it's pretty much B1 plus B2 negative K hat. We can factor out. Now what I have here is B1 is the magnetic field due to wire 1, which is mu naught I1 over 2 pi times the distance. And the distance will be, in this case, 3a, right? Because it's 1a, 2a, and 3a. That's the distance from wire 1. Then plus mu naught I2 over then 2 pi, then the distance here, this distance, which is just a. Okay. That means you can think like, let's say it's R1 and R2, right? In this case, for part B, R1 is equals to 3A, R2 is equals to just A. Okay. So if I do this calculation, then I should be able to, factor out most of those things, right? Factor out pretty much every, let's not forget the direction. So the direction will be negative K hat, right? So if I calculate everything, I should get negative 2 mu naught I, since I1 is also equals to I2, divided by 3 pi A K hat. So it's going to be the net magnetic field will be into the page because both of them are into the page. So they're going to reinforce each other and much stronger magnetic field. And it's going to be negative mu naught I over 3 pi A K hat. For part C, then I'm calculating for point 3. Here's point 3, somewhere over there. That means this is again net magnetic field. B1, I can see here is then plus K hat plus B2 negative K hat, sorry, also plus K hat. That means it's just B1 plus B2 plus K hat. Okay. That means this one will be mu naught I1 over 2 pi A, since wire 1 has only distance A from the point P3, then plus mu naught I2 over 2 pi 3A, wire 2 has a 3A distance from that, then plus K. That means this is pretty much, symmetrical to the part B, which is point A below the wire 2. This is point, A distance above wire 1. So this is just 2 mu naught I over 3 pi A, just K hat instead of negative K hat. So exactly symmetric on the other side. All right, so this is how we can calculate the magnetic field due to two, straight long current carrying wires. Another thing we can do, we can take, let's say, one of those wires, and then we can just bend it and make it a loop like that. And we can then see that there is a magnetic field due to that current loop. And the magnetic field, let's say in this case, let's assume that, this, you can consider a circular wire loop of radius A located in the YZ plane and carrying a steady current I. So we want to calculate the magnetic field at an axial point P at distance x from the center of the loop. That means we basically want to find position, the magnetic field at that position P due to the wire itself. I mean that, wire loop. So what we do here is very similar. So here we just choose a small element. We call that ds. And it has a, you can see, right? So this is that vector ds. And then we have a unit vector r hat in the direction of the point P, right? So this guy over here. And then we can see that there's a distance r for the, where our element is with respect to the point P. Okay. So setting up my equation, it will be dB is equals to mu naught I over 4 pi. Then I have ds cross r hat over r squared. Okay. Now from here, what I can see is that we choose this to be a theta, which is the angle between that r hat makes with the y-axis. And then one thing we have here is, so if I'm looking at this, equation for the Biot-Savart law, this becomes mu naught I over 4 pi. And I'm going to see that sorry, I can write this in terms of magnitude of the first vector times the magnitude of the second vector, which is just 1, then times sine of phi. So the sine of phi is the angle that ds and r make relative to one another. But as I go around in the loop, I can see that those two always going to be perpendicular. That means r hat is going to be perpendicular to ds. So that means phi here is always 90 degrees. That means this equation becomes mu naught I ds, so there's r square, right, over 4 pi r square. Okay. So that's my equation for the dB, which is the magnitude of the magnetic field that I get at that point P. The only thing here is this, that magnetic field that we get is this one right here. Okay, this one right there, which means it has two components. There is dBx and there is dBy. So it has two components. X component will be then dB cosine of theta, because we're talking about this guy over here. Okay. And again, don't confuse theta with phi in this case, because phi was the angle between, in the cross product, phi is the angle between those two vectors. Theta is just the angle that, you know, let's say what we're going to see is that theta is the angle that r hat makes with the, y-axis, which then can be also used to set up the component of the magnetic field. So dB cosine theta, this is then dB sine of theta. Okay. Now, from one thing we can see is that if I choose, for example, this part over here as my element, that magnetic field will be in this direction. So it's going to give me components like this and like that. And then if I go around, I'm always going to get components that going to cancel out. That means, for example, if I'm just making it simple two-dimensional, I can see that those two along the y-axis going to cancel each other. And the ones that are going to be along the x-axis, they're in the same direction, so they're going to reinforce each other. That means one thing I will have here is, if I add up all the vectors in the y direction, I'm going to get 0 due to symmetry. That means the only surviving one is the horizontal component of the magnetic field. That means I can say that this is equals to dB cosine theta, which means mu naught I ds over 4 pi r square times cosine theta. Okay, so let's continue with that. That means I can just pretty much ignore this one. And using that equation, so let's continue here. So then dBx is equals to, so I have mu naught I ds over 4 pi r square and then cosine of theta. Okay, so the way we're going to then rewrite this is mu naught I over 4 pi. Okay, then I have then ds over r squared, which I'm going to write it as x squared plus a squared, just x squared plus a squared because it's r squared, because you can write r squared here is x squared plus a squared. And then I'm going to have cosine theta, since cosine theta is going to be in terms of adjacent over hypotenuse. So then I can rewrite that. So I can say then cosine of theta is equals to adjacent a over hypotenuse, which is square root of x squared plus a squared. That means rewriting cosine of theta as a over x squared plus a squared 1/2. So I'm going to get mu naught I over 4 pi. Then I'm going to get a ds over x squared plus a squared 3/2. And that's my expression. Now from here, what I can see is that if I then go and integrate both sides, the left side is just going to be dB, like let's say, sorry, dx. So the integral of dbx will just give me bx, x component of that. The right side, mu naught I over 4 pi, it's the, obvious choice of taking it out of the integral. But also, you can see the a itself is a constant, it's just a radius. I can remove that as well. I can also remove x squared plus a squared 3 halves. Why? Because as you go around this loop, a doesn't change, x doesn't change. None of those things change. That means x squared plus a squared 3 halves is also a constant, which makes then the only thing I have is just the closed integral of ds. Okay, so then if I do mu naught I over 4 pi, a over x squared plus a squared 3 halves, this integral just going to give me the circumference of that, of that loop. As I go around and integrate, closed integral of ds is just basically 2 pi a. Okay. Which means my expression will be mu naught times I a squared over 2 a squared plus x squared 3 halves. So this, 2 going to cancel with that, just gives me 2. Pi is going to cancel out with that, and that's going to be then my expression. So this will be the magnetic field at point P along the, x-axis. That means, I have some finite distance x, right, from the center of the loop. Okay. Now, one of the things we can see here is that this will be, again, remember the horizontal component of the magnetic field, the vertical components cancel out, and as you go really, really far away, you can look at it in terms of the two conditions, right? What happens is when you go really far away, and then what happens when you get very close to the loop. So here's one thing we can see. So for example, when you get really close to the loop, you pretty much get a pattern like that for the magnetic field. This is something we've already seen before. This is for the bar magnet. That's how the bar magnet gives you the magnetic field. Starting from north, goes and comes back, but it doesn't stop. It actually goes through, goes and comes back, goes through. That means, remember, there is no such thing as magnetic monopole. So the magnetic fields always curl around. There's never termination and start point for magnetic fields. Same thing with the loop. So you can see that if you have a current, for example, that is going counterclockwise, magnetic field then can be used to show, let's say, that is going to be upwards for this particular case. Okay, so remember that right-hand rule that we use, right? So we if you have a straight wire, we did this. So if you have a current up, then thumb is the current, and then you curl your fingers, sorry, you curl your fingers to get the direction of the magnetic field. In this case, magnetic field, let's say, will be counterclockwise. Okay. Now, if we have a straight wire, then this right-hand rule best used when you have your thumb as the current direction and you curl your fingers in the direction of magnetic field. That means thumb is the current, fingers are the magnetic field. That means you curl in the direction of magnetic field. When you have a loop, current loop like this, other way around is actually more convenient. That means you have your thumb in the direction of the magnetic field, and then your fingers will curl in the direction of the current then. So you can see, right? If you have counterclockwise current, magnetic field will be going through the, center of the loop, upward direction. If you have clockwise current, which you can say, right? That means if you have a clockwise current, that means curl your fingers in the direction of the current clockwise, thumb points down, that means magnetic field will be, downward. That means it's easier to see it from here when you have, let's say, magnetic field going through a circular loop like that. Okay. Now, also, in terms of for the circular loop, you can see that you have equation that I just derived for you. That equation gives you in terms of, um, let's say if you have, put like this, right? Or think like this. So if I have this, so through the center axis, right? So some point over here. Okay, that was for some point over there. That means imagine that this is the x-axis, right? So let's say, for example, then the magnetic field was mu naught I times a squared over 2x squared plus a squared 3/2. Okay, that means that will be the magnetic field uh, at that point. Okay, assuming that, let's say, that's basically the z-axis, for example, right? One thing we can have here is you can also have a loop that has what we call a number of turns. In that case, maybe there's a loop with another loop and another loop and another loop. So we can include n as a n number of loops. So you can basically include something like that. Okay. But also one thing we can do here is assuming that this distance x, let's say if it gets closer and closer and closer and closer until it basically gets to the center of the loop. That means it fits along the, you can say, right? So like, let's say, that means we're looking at the magnetic field at that point, at the origin, right? So is that zero? Well, no. According to this diagram, right, it's not zero. That means, there's actually a magnetic field going through that. But this is basically take this equation and say, all right, so then this is when x is equals to zero. So when x is equals zero, that means you're just basically getting rid of this term, which becomes zero. So let's calculate that. X component equals mu naught I a squared times n divided by then 2 times. Well, if then x squared is 0, then this becomes a squared to the power of 3/2, so which gives you a cubed. Okay. All right. So then this will go away with that. Then x component of the magnetic field will be then just mu naught I times n divided by 2a. Okay, which a, remember, is the radius of that loop. That means this is when x is equals to 0. That means at the center, center of the loop. So mu naught in over 2a, and you can calculate that to be the magnetic field for the center of the loop. All right. So here's one more example over here. We can then combine those two things that we just learned. So we're going to calculate the magnitude and the direction of the magnetic field at point P due to the current in the semicircular section of the wire shown below. All right, hint. Does the current in the long straight section of the wire produce any field at point P? That means our goal will be to find the magnetic field, basically the total magnetic field at point P. To do that, we break this down into 3 segments. Segment 1, segment 2, and then this, semicircular is in the segment 3. Okay. So let's look at, segment 1. So for segment 1, so let's kind of get rid of all right. So for segment 1, what I do is just I choose a small element, and let's say that's going to be my ds. Okay. And then this is the distance from that to point P. So let's call that r. Then what I do is that my r hat vector, which will be this guy over here, r hat vector. So for then segment 1, then I have dB is equals to mu naught I ds cross r hat divided by r squared over 4 pi. But here I can see that ds is equals to ds I hat. R hat is also equals to I hat. Well, if I do a cross product for those, I'm going to get 0 because both of them along the same axis. That means that straight portion segment 1 does not contribute to the magnetic field at the center. Let's look at segment 2 over here. Okay, here's for segment 2. All right, so I have my element like this, and this is my ds. Okay, That means if I have dB is equals to mu naught I over 4 pi, then ds cross r hat over r square. Here I can say, right, my ds is equals to, as a vector, is equals to ds I hat. The unit vector r hat, in this case, will be in this direction. And the distance will be some distance, let's call the distance r. Not the radius r, but some distance r. But in this case, still, what I can see is that r hat is equals to negative I hat. Now, this is I hat, this is negative I hat, doesn't matter, right? Both of them along the x-axis. I'm going to get 0. That means both of those straight segments do not contribute at all to the calculation of the magnetic field, okay? Because as long as you're on the same axis, the magnetic field and the current element, right, the dl, you're going to get 0. That means for both of them, ds cross r hat ends up being 0, because I hat cross I hat cross negative I hat, doesn't matter. That cross product going to give us 0. All right, so then finally we are ready to look at the circular portion. So for here, let's say I choose some kind of, segment right there. You can say that this is my ds. This is r, and this is, let's say, r hat. And I can say, right, at all times, this angle phi that r hat is going to make will be 90 degrees, right? That means what I have here is for the segment 3, which is the semicircular portion, I have dB is equals to mu naught I over 4 pi, then ds cross r hat over um, r square. So let's say I have that. But, what I can see here is this. So for this, r is equal to the radius. That means this distance here from the element to the point P is just the radius, right? So r is equal to the radius, and phi is equals to 90 degrees. Okay, so I can have that. Now, also what I can do from here is that it's easier to write it like this: 4 pi I over, sorry, mu naught I over 4 pi. Then I represent r hat in terms of vector r over the magnitude. Okay, so that means I can say that this is ds cross vector r divided by, I already had r squared, and another r over here gives me r cubed, like that. Okay, so basically it gives me r cubed. Okay, so then I can rewrite this in terms of mu naught I over 4 pi, and then this ds cross r vector, now not the unit vector, but vector r, that will basically end up giving me this, right? So then ds cross vector r is basically end up being r dl, pretty much. So if I take that, I can call it like dl or ds, but it's just rdl or rds, same thing. Okay. Because technically there's also sine of theta, sine of phi, but phi is 90 degrees, so we can just ignore that. Okay, so that means this becomes r dl divided by r cubed. Okay, so from here, let's go back over there. I have mu naught I over 4 pi. Then this will cancel out with that. So I have then dl over r squared. And this now can be then integrated. So dB is equal to that. So if I do the integral, I'm basically integrating that. And pretty much everything, including the r, the radius, is constant. So mu naught I over 4 pi and r squared can also come out. So then all I have is just the integral of dl, close integral of dl. So this is going to be mu naught I over 4 pi. Then this is the pretty much the circumference or half a circumference going from let's say point A to point B, so which will give me pi r. Okay. And then pi is going to cancel out. And finally, I'm going to get mu naught I over 4r. Okay. So that's going to be then the contribution from segment 3. But since that was the only contribution, that will be the net magnetic field. Also from the right-hand rule, we can see that in order for the current to go clockwise direction, magnetic field has to be into the page, so negative k hat direction.